Okay, good afternoon, everyone. Welcome to the second part of the August mini-school on the introduction to big data and machine learning for particle physics. And the second lecture of today will be presented by Professor Deepak from WITS and CERN, as you can see from his email address, and Professor Bruce Mellado, who is the main organizer of this mini school. Will now briefly introduce again Deepak for those of you who didn't attend last week. So Bruce, if you would like really quickly in one sentence introduce Deepak, we can then ask Deepak to start with his presentation.
Thanks, Francesco. As you may know already, but those that don't, this mini school is composed of 5 lectures. The first 2 lectures are taken up by Professor Carr, who is introducing basic concepts in machine learning in the context of particle physics. Next week, I will come in with big data and how big data is materialized in particle physics and how it works with machine learning. And the last 2 lectures will be hands-on sessions led by Dr. Ruan, who will go through an exercise and will go through everything that's needed to understand the basic steps from the standpoint of software and how we think when we code and program in this space. So please, Deepak, take it away.
Thank you.
Thanks, Francisco. So I think this is the point we left off. Now, I think because there may be people who are not there yesterday, I mean, I'm a physicist, so my whole emphasis is on how can we use machine learning to understand physics better or make sense of our data better. So that's my focus. And I think this is the point where we stop, that deep thinking is what I would call like what physicists typically do, and deep learning is essentially a generic name for pretty much this kind of AI-based thinking. So where do we meet? So we did talk about decision trees last time as a simple application of machine learning, but I also mentioned decision trees and BDT, which many of you use, boosted decision tree, is a special like a setup for decision trees. It's not new. It's been there for 90s, if not earlier. Neural networks, on the other hand, are comparatively newer. They try to kind of simulate, I mean, that's what we say, like how your brain behaves. But let's try to look at a very simple example, just in case you don't know how it works. So let's assume you have a function y equal to 3x, but you don't know that the factor is 3, and you are trying to find it out by machine learning. So what you do, but you give it an input and you get a certain output. So what you do is, again, this is super simple. So, but I find this, when I first started learning about these things, I found this very useful. But you don't know what this weight or W is, right? This y equal to certain Wx, what y is. So let's start with the W as 2. We don't know how this is. So we give an input, we get an output. So if you give 2, so it's y equal to Wx. So you can see you give inputs of x as 0, 1, 2, 3, 4, and you get twice of that because you set w equal to 2. But then you actually know the actual output you are looking at. Now, in this case, it's simple, it's 3x, but in more general case, we would not know, right? That's what we're trying to find out. What is this number? So then you see the output is actually 3, 6, 9, 12, so on and so forth. So how do you then try to find what the output is? So in machine learning terms, the process I just described is called forward propagation, where you pass x values and you compare to y values. Now, you have to have a way to compare how is your guess performing. So typically you take the square difference, because then essentially you blow up the larger differences and you also want to worry about the sign. So in each case, for example, this w equal to 2, you take the square difference, you sum it, you get a number. And then you try another value of w. And you try to see when the square difference is minimal or 0. So in the little plot here, I mean, if you increase the weight, if the weight is 2, Then if you increase the weight, you go closer to 3, and this difference decreases, which is technically called loss function in machine learning terms. And essentially, the value of W, which minimizes the loss function, will give you the desired result. Now, learning, when we say machine learning, involves rerunning the activation function with different weights, which in machine learning terms, it's called backpropagation. Now, I know this is all very simple, and who is going to use machine learning to find y equal to 3x? But we essentially can translate it into more complicated things. So in the slides, which I'm sure will be made available later, I actually gave some examples, like how you take the derivative of this function, and because derivative kind of gives you the slope. So you know when you are approaching 0, but I'm not going to go into details. So the idea is you essentially make a neural network where you have a bunch of inputs, bunch of weights, and then typically we also call a bias term, because maybe your function was not y equal to wx, but maybe it was y equal to m plus wx, like even if we are sticking with a simple example. And then the bias term essentially accounts for the m, and the activation function is actually the functional form we are using. Now in this simple example, of course, functional form is like nothing, but we'll see. And then you have inputs, you have outputs, you have one output for this example, and you compare the output and you redefine your weights and the bias if needed. And essentially, you try to express the relationship between inputs and outputs as a function. Now, I think this is something which we must appreciate, that not always there is a functional form. We are trying to guess an approximate functional form, which is going to help us to solve the problem. When we have a new set of inputs, we can actually get the output, which would be closest to the model, because we have hopefully have picked a good approximation for the function. And for those of you who are more mathematical oriented, the whole thing can be written essentially as a form of matrix algebra, like matrix multiplication followed by an addition. Now, as I said, a more complicated relationship, which is something you would typically get because nature is not simple. It can be a series of functions. So rather than just having one layer here, you would have more layers and more neurons connecting them. And these are termed hidden layers because you don't see them. So you have an input layer, you have an output layer. Those are the ones you see. And you have different hidden layers in between, which apply different kinds of transformations to try to mimic the behavior of the input against output. So this is an example where you have one hidden layer, which is denoted by the the orange circles. Again, so you have neurons connecting them, then the first hidden layer does something, the second layer does something, and you get the output. And then this thing, you can write it as a form of, again, in matrix, essentially in form of matrix algebra. So the output would be a function, which is the function we are going to use, and then the weights and the initial input. So you can write all of these things, and then the last one is the bias term, so that's that. Now, typically, we use some specific functions which has been found to help us model most of the things we see. So, for example, sigmoid function, I mean, I've shown the pictures of some functions so that we see easier. So these are the functions, like these are some of the functions we use as activation functions in our building our neural network. So when someone says they're building a neural network, it means they're coming up with how many layers there would be, how many nodes there would be, what activation function you are going to use, and pretty much that. So and that depends on a specific problem you are going to target. For a very simple problem, you can have a one-layer network. For a very complicated problem, you might need more layers. But this is something you kind of gain experience with practice, which Dr. Ruan is going to talk about, I guess, on the last lectures. So what are the types of neural network? So ANN, which is a generic term for artificial neural network, which is kind of an example I showed you before. I'm not going to go into that today, but CNN, which is the convolutional neural network, is mostly used for image processing. I mean, who hasn't seen cute pictures of cats and brooms and trying to identify them? So some of them are done by CNNs. And GAN or generative adversarial network is a combination of two, but I'll come to that because we have some examples in physics which uses GAN. So those are the type of networks in a very simple way. Of course, there are more complicated networks now, like graph neural networks and stuff, but to start off, we're just looking at like very basic principles. So types of learning. Now, the description I gave in a couple of slides back, where you have an input and the output, you know the output, that's essentially an example of what we call supervised learning. So we know we have a labeled data set, we know how it behaves, but then we have another data set we don't know. We know it's similar in terms of physics property wise, but we want to use the learning we obtained from the first set on the second one. So that's supervised learning, and that's what most people have been doing for a long time. Now, unsupervised learning, which is the other extreme, is you don't have a labeled data set, but you just look for patterns in data. If some events have a very different pattern, and does that mean something interesting? Does that mean there is new physics? So we'll talk a bit more about that as we go along. Kind of a middle ground between them is called semi and weakly supervised learning. It uses both labeled and unlabeled data. GAN is an example. There are a few other examples as we go along. I'm not going to talk about that in context of particle physics, but people use something called reinforcement learning, where essentially it's trial and error in every stage, and you kind of incentivize the right answer and disincentivize the failures so that algorithm kind of moves towards getting the right answer. I see something in the chat. Is it something important? Because people can still hear me and everything.
Yes, we can hear you. And in the chat, Francesco just invite people to submit question in the Q&A, so you can just continue.
I thought it's something like can't hear you anymore. Okay, perfect, thanks. Okay, so now let's go into some particle examples, because that's what we do. That's how I got interested in this field. And turns out pretty much in every step of a data analysis, you can use some of these techniques. So I kind of categorized it in two broad classes: signal to background discrimination, which can include a lot of things like pattern recognition, object reconstruction, trigger. We'll talk about these things. Searches, like looking at some variables, combining them, like we talked about in case of decision boundaries, jet identification, which is something I work on. And then we can also use something called some of these techniques in simulation. So these are broadly like event generation, detector simulation, unfolding, uncertainty estimation. I'm not going to go into all of that, but let's start with the first. So I think I mentioned very briefly last time, we have literally millions of events coming out of LHC in every second, and we can't record all of them. We can't have, because of our because limitations of our hardware, limitations of our storage. So we employ trigger systems which saves potentially interesting events. Now, can we do it better with machine learning? So I'm definitely not an expert on these things, but FPGAs are like fancy electronic boards, as I understand. And then people use GPUs and FPGAs to essentially improve the trigger decision, make it much faster. The triggering happens in different levels, and people are using, I mean, this is something which CMS is kind of an early pioneer. They have done a lot of studies using GPUs for their level 1 trigger and their high level triggers. So essentially because these are more automated, they essentially reduce the time to process these things, which is a huge bottleneck. And yeah, I think it also helps in parallelization, which makes things get faster. So yeah, I'll come to stuff which I know more about. So track reconstruction is, what are the tracks? When you have charged particles coming out of a collision, it passes different layers of the detector. So in this very simple schematic diagram, you can see these red dots in different, so these are like track hits. So your charged particle passes different layers, makes essentially like how do I say it? Makes a signal at each layer, and those are the red points. So in this simple example, of course, life is simple. You can just feed the tracks with their curve because if they're charged, the more charge they are, or the less energy they have, they carve more. But you can kind of fit this. I mean, there is no ambiguity here in this example. But if you look at the picture on the right, which is a real picture of the Atlas detector with lots of tracks coming out, and then you have a picture at the bottom which has 11. So in the left picture, I just have one collision vertex. But typically in LHC, we get more than one because typically we don't collide one proton against one proton, we collide hundreds, thousands of protons against one proton. Because if you just collide one proton, then once you collide that, you are done. You have to put in more protons in the beam. So we have like beams of like hundreds, thousands of protons. And we try to make sure, narrow the beam so that one proton collides at one proton in the detector, but typically we end up with like, on an average, 30, 40, 50 collisions. So this one has like, right bottom has like 11 vertices and lots of tracks. So the track fitting itself becomes complicated, like which are the unique tracks, and people use pattern recognition algorithms to find out the tracks. And this is going to become way more important in coming years because, as some of you may know, the LHC is going to get upgraded to what they call HL-LHC or high luminosity LHC. So there will be more luminosity. That essentially means more protons, more pileup, more tracks. So efficient identification of tracks or efficient reconstruction of tracks is a critical thing. In fact, a few years back, there was this TrackML challenge, which involved physicists and the machine learning community on Kaggle. So there was a contest, and I don't know if you can see it, but they had like a substantial amount of prize for who could come up with the best algorithm. The next thing I'm going to go into is what we call electron reconstruction. So you know electron, we all know what electrons are, fundamental particles. Now, as we said in detector, even finding an electron, even realizing that electron came out, is not an easy task. It's sure, because it's a charged particle, it gives a track, and it deposits energy in certain part of the detector called electromagnetic calorimeters. So from that path and the energy deposit, there are many, many variables we can construct how the energy deposit, I mean, what is the pattern, what's the angle, how many layers, blah, blah, blah. So again, I'm not going to go into all the details, but there are like many, many different variables we need to look at to make sure this is an electron. And this is a classic case of like optimizing in a 20, 30 dimensional space. So I just put like 3 figures, and a lot of other particles like jets, which are not electrons, also behave in the same way in terms of these variables. So you have a classic signal to background separation problem. And except in one variable, you actually see there is not a huge difference in shapes between all 3. So you combine them in a BDT, in a deep neural network, and you come up with a discriminating variable, which tells you above this value is probably an electron, below this value is probably not an electron, which is a very critical part of our physics program, because you need to know what is an electron to find out if your Higgs boson decayed to 4 electrons, for example. This is something very, very new. So Atlas literally came out with this result called MetNet, or this architecture. So MET stands for missing transverse energy, which I think I mentioned, if you have a neutrino in the event, neutrinos are not seen by the detector. So you sum up the form momentum of all the other particles and you get an imbalance because you miss one particle. And that is essentially what we call as missing energy. Now, of course, neutrino is standard model, but you can have dark matter particles, new physics models, which gives you also missing energy. So we want to understand missing energy better. Now, typically we used some variables to construct our missing energy, but recently Atlas used this thing called MetNet. So it actually gives you a neural network architecture and the hyperparameters for some of you more technically oriented, but it takes into input a bunch of things which are the way we used to calculate the missing energy, and a lot of other variables like number of jets, number of electrons, number of muons, blah, blah, blah. And then what it does is, it actually makes ROC curves and comes up with some efficiency points. So, and they optimize these efficiency points using this neural network architecture. And then they define like, fine, if you really want very pure sample of electrons, sorry, pure sample, like the mate is very pure, then you take the tight net, and if you can get away with some fake missing energy which is not really coming from neutrino or the physics processes, then you do lose. So this is the ROC curve description I showed you last time, that you take different working points, and this is very common in Atlas and even in CMS. Like you decide on some working points with depending on the signal to background ratio. Here, the signal being the real met, the background being the fake met. Now, one of the things I'm really interested in is JETS, and ML for JETS is also a name of a conference which started the last couple of years. So it's machine learning for JETS. So if you remember, JETS are essentially spray of hadrons coming from one single quark and gluon caused by this whole Parton shower thingy. So one quark and gluon gives you like hundreds of hadrons, and you collect them in a conical object called jet, as you see in the picture. Now, classifying jets based on origin is a super interesting thing because this can give us hints about new physics. If a new particle decaying into jets as opposed to a standard particle, or new particle decaying into some other particles that decay into jets. Now, we started off mostly using supervised learning, using simulation, because that's all we had, but we are moving to other things as we'll show as it goes. So jet tagging is one of the most critical things, as we said, depending on the origin. So typically we try to find out if the jet came from a top quark or a W boson, which are heavier particles, compared to light quarks, which are like, let's say, up-down, charm, strange quarks, which are much lighter, or gluons. So jets coming from light quarks and gluons are typically our background because we get plenty of them, and jets coming from top can indicate exciting new physics process, or even if you are trying to do something with tops, they're interesting. So they used BDT and DNN for top tagging, so identifying if a jet is coming from top. And then on the left for BDT, they looked at a bunch of jet substructure variables. So these essentially calculate how energy is distributed inside a jet. And as you can see, on the left plot, as they add more variables, the background rejection increases because the BDT becomes more and more sensitive as you add more nodes to it, if you remember when you talked about decision trees. Whereas for DNN, they did it slightly differently. If you look at the bottom figure, they picked certain groups of variables and tried to use them in the DNN, and they realized that for certain categories or certain groupings, the network performs better, and then they figured the best performance in each case is actually very similar. So in this case, BDT and DNN behaved very similarly. And then this is the one discriminating variable from BDT and DNN, and you can see they look very similar to cutout between QCD and background. Now, one thing you have to realize, even when you apply a cutout, let's say 0, and you say right-hand side is top jet, left-hand is QCD, it's not 100%. There is a background contamination, and the working points take into account that. I have to share it with you, not because I like it, in fact, I hate it. So CMS, which is the other experiment across the ring from us, has a similar physics program, and they also want to tag top jets. Now, they came up with an algorithm which uses every single particle in the jet and therefore momentum, which is something I don't like because it's ignoring all the developments we have by constructing these variables. So each of these variables, let's say on the left-hand side, have been constructed after a lot of effort to discriminate between signal and background jets. Now, CMS is ignoring all of that effort, but they called their algorithm Deep AK8, or if you look at it very carefully, it spells my name. And every now and then, someone, like when they see this, they're like, oh, why CMS named the algorithm on your name? I'm like, okay, I don't work in CMS, and I don't think it would have flown in Atlas. I don't think I could have done that, or we could have done that. That's what they did. But that's probably for me is a classic example of what not to do, even though it carries my name. Now, the other thing in jet tagging, which we worry about, is what we call mass decorrelation. What do you mean by that? So typically what happens is, if you are looking to find a top quark jet from a light quark jet, you know the mass of the top quark, right? Because top quark is a standard model particle, it has a mass of around 175 GeV. So you apply a cut, you only take jets which have a mass close to top quark when you are looking at background, because you clearly don't want a background jet of mass 500 GeV or 30 GeV, because that won't be misidentified as a top just based on mass. Now, what we see is, when you do the selection based on mass, the background shape kind of starts looking like data. And this feature is called background sculpting, because you are essentially picking very similar physics events, even though they're signal in background. So that's okay when you are doing top. I mean, that reduces your efficiency of the algorithms. But this is really bad if you are looking for a jet which is coming from a new particle. We don't know the mass. But then the background sculpting would really make our search very inefficient, because we do search in different mass ranges, and we don't want to do that. So we try to come up with different techniques. I think one of my master student, Kokotla, who worked on this with me, tried to decorrelate the mass when training. And I think we had some initial encouraging results, but the master's finished. Maybe we'll follow up on that later. So essentially in this project, we applied some Lorentz transformations to decorrelate the effect of mass. Now, this is something I'm working on now, jets as images. So a jet, on the left-hand side, you can see there is two jets coming out of the collision. If we have a cross-sectional view, and then if you look at the energy deposit of the jets in different parts of the detector, you can represent them in a 2D picture in eta phi plane. Remember, we talked about in our collider, we have two coordinates, eta and phi, two angular coordinates. You can think of them as x and y if that makes life easier, but they're angular. Eta phi, and then the intensity of each pixel kind of depicts how much momentum or energy each point has. So you can depict a jet in terms of an image. Now, why this is useful? Because we actually have a toolkit to distinguish between images, even when they're subtly different. And the image contains all the information from the original jet, the energy deposit, the angular spread of each constituent. So this is something which is becoming very, very, very relevant right now. Now, there are a few things we need to do. We call them pre-processing, to use the jet as images, because computers are dumb. So you want them to do the least amount of work for you. So what we try to do is we try to kind of cast the jets in the same form. By that, what we mean is we try to put the highest energy constituent or highest energy particle in the jet at the center, and then we try to put the second highest maybe at one specific side, so that the machine learning algorithm or the image discriminating algorithm does not get hung up on features which are just random fluctuations between different signal events, rather than it can focus on the real physics differences. And then, yeah, so that's what we do in pre-processing. There are a few steps we do. And this is a picture of jets from a few different processes. So gluons, up quarks, charm quarks, and B quarks. Again, by eye, they don't look significantly different. They're not supposed to, but there are subtle differences which image processing toolkits can exploit and try to figure out which one is which one. In fact, I would show you a picture of boosted top jets, because that's something I have been working on. And you can see the top is the right-hand side and the background is left-hand side. Of course, when we show these pictures, these are not individual jet images. These are like sum of thousands of jet images for representational purpose. So in the machine learning, we pass individual jet images as labeled data set to start off with. But when you're looking at these things, because as humans, we don't want to look at hundreds of images, thousands. So we like squash them and like make one image. But you can see there is some difference between a QCD and a top jet. So that's what CMS has been using. Now as we speak, we are involved in a summer project with two summer students. One guy is from Belgium, another woman is from from Russia, and we're working with them with my postdoc Tasnova and PhD in Anaconda to discriminate what we call semi-visible jets, which is a unique dark matter signature. I'll leave it at that, which is something we are looking at in Atlas. But the main analysis doesn't use this yet, but we are kind of doing a feasibility study. Now you can see, the left, I think, is the signal, the right was the background, but they look very, very similar, at least at the first glance. But this is the project with undergraduate students we are doing, and we're going to carry it forward. So that was ML for jets, or how we use different techniques to distinguish jets. Now, of course, we use these techniques to essentially distinguish signal against background. I'm just going to give you one example. So TTH discovery, what is TTH? Higgs boson, as you know, is our crowning glory in LHC. It's a new boson which was discovered in 2012, predicted many years back. Now, the production of Higgs boson with two top quarks, a top-anti-top pair, is one of the most difficult processes. But it's also a very interesting process because it kind of gives us a clue about how the Higgs boson couples with two fermions through top quarks. So after the discovery, for many years, Atlas and CMS have tried to measure this process, observe this process, have significant number of events with TTH. And this was difficult because it's a very complex final state with lots of jets, lots of leptons. But I think this was like a few years back, 2018. Atlas finally managed to get like a 5.8 sigma significance. So they observed this process. And as you can see, they used a bunch of variables, put them in a DNN. And individually, maybe except one, none of these look very promising. And there are correlation among them. But they used all of this. And then they came up with a discriminant, which helped them to get enough data events which they could uniquely identify as TTH. So that was good. Now I have to do this. You have been using BDT and DNN in searches, and we are going to use them. I mean, no one is running away from them. But they depend critically on simulated samples. And us who are working on LHC experiments, we know the simulation is not perfect. I mean, it's great. In most cases, it's probably like within 5%. But there are corners of phase space where you would expect the new physics to hide, because those are the spaces we haven't looked at. And there the simulation may not be so great in all cases. But if you are completely reliant on the simulation while training these algorithms, then that might bias us. So how can we be less reliant on simulation? So a class of algorithms, at least in particular, we call them broadly in terms of anomaly detection. So we try to use data as much as practicable. Now, there are issues using data for searches because so typically we blind the signal region where you expect the new physics signal to be, because you don't want your analysis strategy to be biased by that. So you try to do an unbiased search, optimize your selections based on simulation, and then look at data and see if there's a new physics signal or not. So we have to be very careful when we do these things, but we want to train on data. I'll give you one example. So anomaly detection in general seeks to identify few events or even samples, if you're looking at few mixed event samples, which are not exactly identical to the other part, and that might give us something. So one of the algorithms which became quite famous last few years is called koala hunting. No cute koalas were harmed in this process. So people looked at a very simple process called dihedral resonance, which essentially means you have a new particle X, which may decay into A and B, and A and B essentially giving you jets. So from the A and B jets, we're trying to see if X is something unexpected or X is just, there is no X, it's just standard model jet production. It's a complicated process, but the idea is they come up with two mixed samples. One is more signal than background, which is of course artificial. The other one is more realistic, with mostly background. And then, okay, so B and C are their jets. So I think they call A is the main heavy particle, B and C are the jets. So what they do is they look at the MJJ, which is the invariant mass of the two jets we are looking at. And then they are essentially trying to see, like, there is a signal region, which is the mixed sample one, but then they try to look at what they call sideband region, where essentially it's a mixed sample two. I don't expect a signal. So let's look at an example. They did it in Atlas. So we call this search as bump hunt because, as you see in my picture, it's a bump over the continuously falling background. So they looked at the range of 1.8 to 8.2 TeV, which is a huge range. And then they divide it into bins. And the lowest bin, they assume there is no signal there. And then they essentially use the bins to train the neural network to say, oh, this bin has no signal. Does the next bin has any signal? Once that bin is ruled out, they can like kind of iterate and progressively move towards higher PT bins, like eliminating bins that there is no signal. I mean, I know this is a very simplification of this model, but this is, yeah. So essentially they, for each iteration, they did like a central signal bin and sidebands, where the sidebands you don't expect any signal. And then in the central bin, you are trying to see if there is any signal. So this is mostly based on data, which is great. I mean, they validated the method in Monte Carlo in the simulation, but the actual search was based on data, which is great because then you are not affected by intricacies of the Monte Carlo. And yeah, so then they injected signals. What essentially means is they put some simulated signals and try to see if the algorithm catches it. Turns out it did. You can see this 2D correlation plot. So they looked at the correlation between two masses of two jets. So that's good. And then they set better limits on this process compared to other searches. And so with my master's student, Roy, who just submitted, we tried to look at anomaly detection methods, different anomaly detection methods for the same visible jet and the dark jets, which are like specific dark matter models. So he just handed in the thesis. We checked a lot of methods, including this Koala. So, and hopefully we can use some of his conclusions in Atlas. I don't have a lot of time, but I'll try to cover the second part of my talk, which is simulation. So event generation, detector simulation, unfolding, one of these things. So event generation is essentially making simulated events. It's a multi-step process. First, you calculate the exact collision event, protons coming in, stuff going out. And then the next step is a detector simulation, because these particles interact with the material of the detector. And that's actually more of a nuclear physics problem in some way, but this is computationally very expensive. And in our simulation process, this actually takes the longest amount of time. So can we make each of these two steps using machine learning? Now, for event generation, people have looked at using this with GAN. Now, what is GAN? And this is something I find very interesting. So this is essentially two neural networks competing against each other. I mean, think of it as someone is trying to counterfeit money. So you have your money, the real money. So maybe you have an algorithm which is trying to print new money, trying to stay as close to the original design as possible. And then you have a neural network which is trying to say, like, is this money real or fake? Now, they're doing it in a loop. So the person who is trying to identify the counterfeit, or the neural network is trying to identify the counterfeit, is getting better and better because he is getting like more sophisticated fakes. Whereas the person who is making the fake also improving because he realizes if the fake is not very good, it would get discarded. So event generation is kind of like that. You try to generate some events, the 4 vectors of the events, and then the other part kind of looks at a lot of distributions. No, they don't look physical. Your PT doesn't fall steeply. Your eta is not symmetric. Try again. And so by this back and forth, the things, the generation becomes more appropriate. So that's what is happening. And that's what people do for event generation. I mean, here people compared, I mean, it's a very simple distribution of PT of top quark. The shape looks fine, but when you compare it with like a true physics event generator with the simulation, with the GAN output, they don't really look identical. I mean, there is a large undershoot there. So, no, sorry, yeah, the shape kind of becomes. But of course, there are many subtleties because when you generate events, you're just generating the 4 vectors, but then you have to construct many physics distributions, and they should all look same. When you are actually inputting physics in the generators, that's easy. But when you are just asking it to generate 4 vectors following the standard constraints, energy, momentum, and everything, then of course it's more complicated. But people are getting there. I think I'll skip that. So for the actual detector simulation, it is essentially shower of particles in different layers of the detector. And they use jet images, and they use GANs. They use something called CalOGAN, which is essentially a GAN modified for this image checking or image generation and checking. And then they compared with GIANT, which is our standard way of generating these things. And things don't look too bad. They're not perfect. We are not there yet, but Atlas is trying to do that. And the other advantage is, even if they're not perfect, you get a huge computational speed up, which is critical for the experiment as we go to HLLHC. The last thing we're going to talk about is unfolding. So when we measure something in data, it's always a detector level because we measure things in a detector. However, for measurements, it's beneficial to present the results correcting for the detector effects, or we call it a particle level. Unfolding is a generic name of processes which does that. If you ask your mathematics friends, they would say this is a badly posed problem because there is no unique solution. But we have many methods, bin by bin, SVD, Bayesian unfolding. So a few years back, my postdoc Debarati and I, with a collaborator, we wrote the first machine learning based unfolding paper. And you can see like the results actually compare reasonably favorably with the standard algorithms. Now, unfortunately, that paper, I mean, we had the first paper, but our method was not very fine-tuned. And we got a bunch of referee comments which we could never really implement. So the paper never got published, but I checked, it has 25 citations now. So everyone who is doing machine learning-based unfolding, like this OmniFold guys, which is now the state of art, they cite us. So it feels good, but we never got that published, sadly. So the OmniFold, they actually don't try to do it distribution by distribution. They try to unfold the whole spectrum so that they can construct any observable from that. It's also using something like GANs and stuff, but I'm not going to go into the detail. So essentially, I'm going to end up with this slide. I mean, and this is very important for me. Like, we have to be picky about where we are using machine learning. I mean, we have this famous expression that you are using a cannon to kill a mosquito. Sometimes looking at things, it feels like that. But there are a lot of ways, as I've shown you, where machine learning really helps us. Makes our analysis more accurate, makes our analysis faster, makes object identification and jet identification much more robust. And then with this anomaly detection techniques, we can do the semi-supervised, weak supervised things, or even unsupervised things where we can actually look for new physics in data directly. So there is a lot of potential of using them in particle physics and beyond, of course, but we have to be careful. And the other thing is, as a physicist, a lot of times I'm also trying to go into the opposite direction. Sure, use machine learning to figure out the best solution for your problem. But then can I learn something from the machine? Why did the machine come up with this combination of observables as your discriminator? Is there some physics in it? Could we have found it? Or do I learn something from the machine? So that's kind of a new paradigm now in this area. Like, sure, you use your state-of-the-art machine learning algorithms to do your analysis, search, whatever. But then what does it tell us about physics? What physics can we extract from this? So that's, I think, where I'm going to leave you. I know that's a lot we covered, but hopefully this gives you motivation, the students who are connected, to look back at different things. And as I said, I'm happy to answer questions. I'm sure Bruce and Xifeng will follow up from there in next week. So thank you.
Yeah, Deepak, thank you so much for the very clear exposition of in this second lecture of the series. I don't see at the moment any questions from our participants, but maybe while they think. and since we are not so many, they are most and welcome to raise their hand, and we can give them the rights to speak. Maybe the other panelists have some comments that they would like to add, or some remarks that they would like to make.
Yes, so first,
please, Xifeng, please go ahead.
Let's see it. If anyone that you have questions, you can just press the raise hand button, and then we can see. Yeah.
Yes.
Okay, Deepak, could you please just go back a bit? I think it's a bit of maybe slide 10 somewhere. You have this distinguish between that one. The next page. No. Next page. Yes, here. So it's an octet. The page, I think it's page 97, 2 pages ago. No, 97.
The other 2 pages, the other direction.
I just wonder that, for example, if you look at this figure as octet to the QQ prime, or the singlet, so you looking by eye, that seems there's no difference. So how can you assure that you use machine learning can make it any discriminant power here?
Deepak, you're muted. You need to unmute yourself.
Oh, sorry. Yes, thank you. Yeah, so you're right, Xifeng. This looks very, very similar. And by human eye, I don't think we can distinguish them, as you rightly said. But if I'm looking very carefully, I'm just thinking aloud here. Let's say, let's look at these 2 pixels and these 2 pixels, right? They are slightly different. So maybe like a good image processing algorithm would pick out these things. Maybe. I think that's what we are going for, right?
Oh, you can see that the color distribution is slightly different because of the figure that the color become green or blue faster than the right one.
Yeah, maybe. I mean, again, I mean, you can't always say there would be a good result. I mean, so this is what, as I said, this is what we are looking at with some students now, and they look very, very similar. Even I can't make the statement I just made, but we'll run some CNNs and see what happens.
Yeah, so you need to check the row curve, the actual row curve, how they can distinguish your sample, right?
Exactly.
Yeah. And actually, based on this, do you have any idea about the numbers that comparing use the traditional method for all of this study and with the best machine learning, how much improvement you can achieve usually?
So I can give you one number because top tagging is something which is very close to my heart. So before we started using machine learning based top tagging in Atlas, we used something called short reconstruction, which was kind of my baby in Atlas, right? And then I think at the 70% efficiency point, I'm just picking one point, we probably had like 20% background. I'm just trying to remember the numbers, 20 or 30%. And then when they moved to this machine learning best stackers, BDT or DNS, they're very similar. I mean, we got bitten. We got bitten because at 70%, I think it background kind of went down by a factor of 2 or something. So you can get large improvements. Of course, you can then include the short reconstruction was not part of that machine learning best stacker. It's not even now. So maybe you can even improve it more. But I think a lot of times we can get, because we always work with like these working points, right? So so the background you do get significant improvement.
Okay, thanks. But if you use the previous example, it's a 70-30 to 70-15, if I understand correctly.
70-15 or 20, I don't remember the exact numbers, but
it's like,
it was significant. It made me very sad because it beat my algorithm.
It depends on how the ratio of the signal and background. So if it's the background is very large, then this is a lot of improvement, 25% at least. Yeah.
No, you can see the rock curve. The rock curve is pushed more to like top right, and you know that. Yeah.
Yeah, depends on how actually the working point it is. Yeah.
Yes, exactly.
Anyone else has
students, no question is a dumb question.
Yeah. And the students are welcome, or the participants. I see some participants are not really students anymore. Are welcome to raise their hand and ask their question. Yeah, and we can allow them to speak.
Actually, not necessary to ask a very, very professional questions. I know that many people may not be the real expert of the Atlas. You can just ask very fundamental questions like how I don't understand that what this curve means, this figure means. You can also even ask this.
And I'd be the first to admit that I can't explain all of this. I'm not an expert in all of these techniques which I showed. I just wanted to have a sample of things we do.
So we can help.
Yeah, sure.
The only question that was in the Q&A was about where to find the recording of the previous lecture, and I just typed in the answer in the chat. Yeah. And
feel free to email me, as I said. I mean,
yes.
If anyone is also looking for like a nice project or something, I mean, they can also email any of us. I mean, all of us work on slightly different topics, including machine learning and physics. So yeah.
Yeah, yeah. No, and I'm sure there will be plenty more questions when we start probably the practical part, because that's what people traditionally are very keen on to read. Here come the first questions. Excellent. Then Ziad, you're welcome to pose your question. Just unmute yourself. Yeah.
Hi, good day, everybody. I'm not from a physics background, or from a electronics engineering background.
Nobody is perfect, huh? Yeah.
Thank you. But I just wanted to find out is, I know you mentioned a backpropagation algorithm that was used, and I think there are other algorithms that are also used, you know, for artificial intelligence or for compiling neural networks. Have those other algorithms been explored also? Maybe more, you know, more recent than the backpropagation algorithm. Like I think something that's referred to is extreme. Is it extreme learning or something like that? Thank you.
Yeah, no, thanks for the question. Yeah, as I said, I'm not a computer scientist, so I think the way I tried to explain backpropagation is just by giving a very simple example of how machine learning algorithms work. Now, clearly, you are right. I mean, there are a lot of new developments and a lot more cutting-edge algorithms which use, I mean, similar terms or more advanced terms. So, I mean, Xifeng, if you know anything about this, feel free to comment, because I haven't seen this, but yeah, I'm sure it exists.
And so let's say, so firstly, you know that the several part of this machine learning optimization, right? Firstly, you need to select the method. So different methods, they have different optimization and the kind of optimization at all, right? And if you talk about like the neural network that this backpropagation is just a default thing, and then you need to know that the optimization function, also the loss function. So which function you're going to minimize or maximize, right? And then you use this backpropagation to define that this function with some constraints, so say this regularization, right? This is a very standard thing. So I just to say that that for the different and the different neural net methods, you can configure the different things like all of this propagation function, like activate function, and also define that different loss function and define all kinds of different this regularization functions, right? And so then the next question is just about how to optimize a given function if you already well define the function, how to optimize that you have this gradient searching or something, some other method. So I just wonder that which part you're asking. You're asking that how to optimize or how to define the function, because the backpropagation is more like that how you define the function, right? Or you are saying that you have a totally different method that not relying on the structure of the neural network, that you can define a totally new thing.
Okay, no, thank you. I understand. So it comes down to fundamentally it's the same application, but just different ways of optimizing your output or your result. Okay.
Yeah, about optimization, that you have all kinds of different methods, that the searching routes, that how you quickly find the maximum point and avoid the local minimum, local maximum, like that, right? And about to build your loss function is another story. But of course, that you choose a better loss function, it will help you to converge your to your minimum or maximum points easily. Yeah.
Thank you.
Okay, thank you. We don't seem to have any more questions. So since we will meet again next week, and if questions arise, I'm sure that the team will be able to answer questions next week as well. So Deepak, thank you so much for another very nice and informative lecture. And thank you also to Professor Mellado and to Xifeng Ruan for joining us, for supporting you. Yeah, no, thank you very much. So next week we will have the lecture by Professor Bruce Mellado, who will address more the big data aspect of machine learning for particle physics and high energy physics. And that will be followed then by the last two lectures on the practicalities of running machine learning codes in Python using all the usual software packages. So thank you very much, everyone, for being with us again this afternoon. Soon as possible after the talk, we will upload the video on our YouTube channel, where you will be able to watch it again if need be, or where you can recommend it to others who missed the lecture today to catch up. So thank you very much, everyone. Have a good afternoon, and we are looking forward to see you next week for part 3 of this mini school. Thank you very much. Thank you, Deepak, thank you, Bruce, and thank you, Xifeng, for your time and for your big effort to put this together. Thank you very much.
Thank you.
Thank you. Bye-bye.
Bye. Stay safe.